Gravity can make a galaxy in a few 100 million years, then spend the next 10 billion very slowly editing what it just built. At the largest scale, a galaxy is not just a pretty swirl of stars, it's a three-part machine: a deep, invisible well of dark matter, a reservoir of gas that falls into that well, and stars that ignite from that gas and then violently give energy back. The dark matter halo is the hidden scaffolding. It doesn't glow, it doesn't collide or clump like normal gas, but its gravity dominates. Our own Milky Way probably sits inside a dark matter halo, more than 1 million light-years across, with 10 times more mass in dark matter than in all its stars combined. This invisible structure decides where gas can collect, how fast it falls, and ultimately, how big and massive a galaxy is allowed to become. Early in a galaxy's life, cold gas from intergalactic space rains down along the cosmic web like rivers feeding a lake. This gas is mostly hydrogen and helium left over from the Big Bang at just a few tens of thousands of degrees, actually cold by cosmic standards. As it falls into the halo's gravity well, it accelerates to hundreds of kilometers per second. Some of it shocks and heats up. Some of it stays relatively cool and sinks deeper. Conservation of angular momentum. Basically the same principle that makes an ice skater spin faster when they pull in their arms, forces this inflowing gas to flatten into a rotating disk. This is the raw material of a galaxy, a giant, slowly spinning turbulent cloud tens of thousands of light-years wide. Inside that disk, gravity starts working on smaller scales, regions that become slightly denser than average, maybe only a few percent, feel a bit more gravity, pull in more gas, and snowball. These are giant molecular clouds. Cold, dense complexes of hydrogen, often dozens or hundreds of light-years across, with millions of times the mass of the Sun. When parts of them get dense enough, their own gravity overcomes internal pressure and magnetic fields, and they collapse, the cloud fragments, into smaller clumps, each forming a star or a multiple star system. This is how a galaxy turns gas into light. In a typical spiral galaxy, only a few percent of the gas ever becomes stars every billion years. Star formation is inefficient and slow, more like a drizzling tap than an explosion. But the stars do not quietly accept their role as passengers. The most massive, short-lived stars pump out intense ultraviolet radiation and powerful stellar winds, fast streams of charged particles. Within a few million years, they explode as supernovae, releasing about 10 pounds 44 joules of energy in a single event, briefly outshining an entire galaxy. This energy slams into the surrounding gas, driving hot bubbles and shockwaves hundreds of light-years across. Collectively, thousands of supernovae over millions of years create galactic fountains. Gas is blasted out of the disk, rises into the halo, cools, and then rains back down. This feedback regulates the galaxy. It prevents gas from collapsing too fast, spreads heavy elements like carbon, oxygen, and iron, and in some cases can even push gas entirely out of the galaxy, starving future star formation. So galaxies grow by a constant negotiation between inflow and outflow. Dark matter halos pull new gas in from the cosmic web. That gas cools and forms stars in rotating disks and bulges. Those stars, especially the biggest and shortest-lived, pump energy back into the gas, stirring it, heating it, and sometimes ejecting it. Over billions of years, this feedback loop shapes the galaxy's mass, its color, even its morphology, whether it stays a graceful spiral or becomes a more diffuse, quiescent system. But this growth by negotiation becomes far more dramatic when galaxies stop evolving alone and start colliding with their neighbors.